All right, so some definitions here. All right, continuity at a point. A function f is continuous at a if the limit as x approaches a of f of x is equal to f at a. Okay? So that means you don't have a hole in the graph at a. You don't have an asymptote. That means that whatever everything is, whatever the y values are that's approaching that x value, it's the same as what the function value is at x. When that's true, it is continuous at that point. All right? All right, so continuity checklist. In order for f to be continuous at a, the following three conditions must hold. All right, so f of a is defined. Okay? So if you plug in a and it makes the bottom 0 or something, that's not going to be continuous there. Okay? The limit as x approaches a of f of x exists. Okay? And the limit of x approaches a of f of x is equal to f of a. So the value of f equals the limit of f at a. Okay? And here are some examples. Okay? So notice this value here, when x is 0, that is not continuous. All through here, though, it is continuous. It is not continuous there. Okay? It is not continuous here because that point is out there, right? It is not continuous at 3 because we jump from here to here. The limit is not the same on both sides. Of course, at that vertical asymptote, it would not be continuous there. Okay? So any questions about that? Okay? Continuity rules. Okay? So if f and g are continuous at a, then the following functions are also continuous at a. Assume c is a constant and n is greater than 0 is an integer. Okay, so if you know that f and g are both continuous, the two functions, if you add the two functions together, you get another function that is continuous. Okay? If you take a continuous function and multiply it by a constant, you get another continuous function. Same thing is true with subtraction and multiplication and division, provided that g does not, whatever g at a value does not equal 0. Okay, and then the same thing true if you raise it to a power. All right, so any questions about that? All right, Theorem 2.10, polynomial and rational functions. Okay, now if you remember the graph of polynomial functions, they're always, every x, you can always plug every x in and you always get something out, right? And there are no asymptotes, there's no holes or anything like that. So a polynomial function is going to look something like this. You'll go down or up on one end, you'll have some curves in the middle, and then go up or down on the other end, right? So it is continuous everywhere. Polynomial functions are always continuous everywhere. So what it says here, polynomial function is continuous for all x. Okay? A rational function, all right, that was a lot of what we were looking at a minute ago in 2.5, where you have a polynomial divided by a polynomial. It is continuous for all x for which the bottom does not equal 0, right? Because when the bottom equals 0, you have either a vertical asymptote or you have a hole in the graph. So it's continuous everywhere except those places. Okay? Any questions about that? All right. Continuity of composite functions at a point. If g is continuous at a and f is continuous at g at a, then the composite function is continuous at a as well. Okay. Limits of composite functions. All right, so if you're trying to take the limit as x approaches a of f of g of x, that is equal to f of the limit as x approaches a of g of x. Okay. We probably did some like that in the last section. All right, any questions up to that point? All right, now this is something to look at as far as the definition goes that he uses here in the in this text. Continuity at endpoints. Okay, a function f is continuous from the right at a if the limit as x approaches a from the right is equal to f at a. And then it's continuous from the left at b if the limit as x approaches b from the left is equal to f of b. So notice here on this graph, you would say this graph is continuous from the right at this point a because the limit as x approaches a from the right is equal to f of a. So if you've got a dot filled in there and you're going this way, you say it's continuous from the right. Okay? Here, you've got the point on the right, but you're going from the left, so you would say this would be continuous from the left. Okay? Everybody follow that? So just look at where the point is filled in, where you have a point, not a hole. All right. So this you would not say is continuous from the right because it doesn't include a there. F of a is not equal to the limit. Okay. So there'll be a few questions, and at least in the homework, where you'll say that continuous from right or left. All right. Any questions? All right. Continuity on an interval. A function f is continuous on an interval I if it is continuous at all points of I. If I contains its endpoints, continuity on I means continuous from right or left at the endpoints. Okay? So here we would say continuous from 0 but not including 0 to positive infinity. Okay? We would say over here it is continuous from negative infinity all the way up to 0, including 0. So that would be continuous from the left because it includes that dot there, that point. All right? So any questions about that? Okay. All right, got some more stuff here. We don't really have that many problems, I don't think. And get through all these. All right. Continuity of functions with roots. Assume n is a positive integer. If n is an odd integer, then it is continuous at all points. All right. So remember, if you have that, what does the cube root function look like graph? Remember that from the 21 graphs? You know, you got it goes like this and up like that. So you've got it. It's going both directions. That is always continuous everywhere. Right? Because you can plug in values for x that are negative as well as positive. If n is even, so like if you have a square root or a fourth root or a sixth root, it is continuous at all points a which f is continuous and f at a greater than 0. Okay? So if it's even, it's only going to be that one side. All right, any questions about that? All right, theorem 2.14, if a function f is continuous on an interval I and has an inverse on I, then its inverse is also continuous. Okay, so if you have a polynomial function and you find its inverse should be continuous as well. Transcendental functions, the following functions are continuous on all points of their domains. Okay, so these are all smooth graphs as long as you are looking at whatever the domain of the function is, right? So sine x and cosine x, those are those waves, right, that go forever from negative to positive infinity. Those would be continuous everywhere, right? Tangent and secant, they have vertical asymptotes at pi over 2, 3 pi over 2, negative pi over 2. So they are continuous everywhere except at those vertical asymptotes. Cotangent and cosecant, they're continuous everywhere except their vertical asymptotes, which would be at 0, pi, 2 pi, so on and so forth. Okay? Questions about that? The inverse trig functions, they would be continuous just on those restricted domains that they have. Okay? Exponential functions and logarithmic functions, you can look at their graphs. Those should be continuous everywhere. All right? Because exponential goes forever. You can plug anything you want to in for x. Now, logarithmic, not. Logarithmic, you cannot put 0 or a negative in for x, so it would only be continuous past 0. Okay? Any questions about that? Okay, last thing is intermediate value theorem. We'll come back to that and that. All right, let's do a few problems here. All right, look at this first one up here. Determine the intervals of continuity for the following functions, and which endpoints of these intervals these intervals of continuity is f continuous from left or continuous from right. Okay. Let's see if I can write this up here. I think I can. All right, can y'all see this from way over there? Maybe? Okay. So I'm just writing the intervals that it's continuous. All right, so notice here it would be a continuous from 0 up to 1, right? But 1 is a vertical asymptote, so it would not include either one of those. Okay, so I would say 0 to 1, okay? And then 1 to 2. Okay, you see that? And then from 2 to 3, right? And it would be continuous here from this 2 to this 3. So I'm going to include 2 on that one. And then 3 to 5. All right, now the sharp curve is all right as far as continuity goes. When we do derivatives, that will not be the case. But for this, we'll say from 3 to 5. Okay? So that would be my intervals that graph is continuous. Any questions about that? Now, where would it be continuous from the right or from the left? Where do you see a definite endpoint? When x is what? Isn't that a definite endpoint? At 2, so you could say it's continuous from the right at 2. Okay? So we would say continuous from right at 2. All right? Any questions about that? Okay. All right. Determine whether the following functions are continuous at A. Use the continuity checklist to justify your answer. Okay. So we'll look at a few of these. I want to notice that is a rational function. If it is a rational function, I've got x's in my denominator. Wherever the denominator is 0, that's going to be either a vertical asymptote or a hole. And it will not be continuous at that point. So what I could do here now is really just factor the denominator. I don't need to worry about the numerator will factor, but it really doesn't matter for this question what it's doing. So I get that. Okay, so the question is it continuous at a equals -5? So when x is -5. Is it continuous at -5? Nope, because it makes the bottom 0 right there. That's going to be a vertical asymptote. So I would say the function is not continuous there. Okay, questions about that? Okay, is it continuous at a equals 5? Well, what has to be true? Well, f of 5, I mean, has to be equal to the limit as x approaches 5 of the function. Is that true? Yes. Where are the vertical asymptotes here? Or where is it not defined? It's not defined at -5 and 0. It is defined at 5. So f of 5 has got to be the same thing as the limit as x approaches 5. So this we could say is continuous at a equals 5. So it's not continuous at a equals -5. And I probably should include that here. But it is continuous at a equals 5. All right, so any questions about that? All right, what about that one? Is it continuous when x is 1? What happens if I plug 1 into that? I get square root of a negative, which is not a real number, right? 1 is not in the domain of that function, all right? So it is definitely not continuous at 1. And you could say because 1 is not in the domain. All right, it's not defined at 1. Okay? We want to know, is this continuous at 1? Okay, that's the big question. Everywhere else should be good, but what about 1? Okay, well, for it to be continuous, f of 1 has to be the same thing as the limit as x approaches 1. Okay? So first, what is f at 1? What do I plug 1 into, the top or the bottom on this one? Which one do I plug it into? F of 1, the top is when x is not equal to 1. So you plug it in the bottom one. If I plug it in the bottom one, what do I get? Always get 3. So f at 1 is equal to 3. Okay? I need to know, well, what is the limit as x approaches 1 of f of x? Okay? Well, as it approaches 1, you would have to look at this, all right? So, because that's f of x equals, that would be x plus 1, x minus 1 over x minus 1, and those would cancel. So f of x equals x plus 1. So the limit as x approaches 1 would be 1 plus 1, which would be 2. So what you're looking at here really would be a line that would really be the graph of the thing. Okay, so this rational function, everything for x you plug in there except when x, everywhere that it's not 1 would be everywhere out here, right? When it's 1 though, it's 3. Okay, so is that continuous at 1? No, because the limit as x approaches 1 of here, what is this actually approaching? It's approaching 2. But at 1, it's actually equal to 3. So these two are not the same thing, so therefore it's not continuous at a equals 1. And of course we want to know, is it continuous at 3? Okay? So just like the last one, we want to know is the limit as x approaches 3 the same as when f is the same as f at 3? That's really the question, okay? So the function value at 3, well, when it's 3, you actually use the bottom one. F of 3 is going to be 2, okay? So I just need to know, well, what is the limit as x approaches 3 of the function at the top. Okay, so I think that will factor again like the last one. I get that, and then that would divide out. So I get the limit as x approaches 3 of x minus 1. All right, well, now that that graph is aligned, this has a hole in it. If I plug 3 into this, 3 minus 1, I get 2. So notice the limit as x approaches 3 is 2. F at 3 is 2. So what is true about this function at 3? Those are the same. It is continuous. Okay? All right. Any questions about that? Okay. The next couple of questions, the directions say, determine the interval on which the following functions are continuous. Okay. So let's take a few of these here. So where is the function continuous? Okay, so p of x, that is a polynomial function. What's true about polynomial functions? They are continuous everywhere. Okay, there's no breaks in the graph, there's no asymptotes, any of that. So this one we would say is continuous from negative infinity to infinity. Domain is everything, and it's definitely continuous on all of those. Okay. Now the other three are rational. So they could have vertical asymptotes or holes. Okay, and they would not be continuous there. So we need to see, all right. So this one I noticed that will factor. The top will factor to be that, okay. The bottom, I have x plus 2, x minus 1, okay. Now, there's no reason to reduce it, because if you have a hole in the graph or if you have an asymptote, it is not continuous there, okay. So notice at negative 2, do I have an asymptote or a hole at negative 2? Does x plus 2 cancel out? No, there's not. You have one in the top, so it is a vertical asymptote. X minus 1, does that cancel out? Yes, so what I have right there? A hole in the graph, right? Either one, it's not going to be continuous there. So here I've got negative 2 and positive 1, or would be the x values that would make the bottom 0. So, I'm sorry, that should be a 1, not a 2. Did y'all see that? Yeah, I was not say anything today at all. Just sit there and look at me. All I see is your eyes, and I don't know. Okay, so anyway, sorry. That should be x plus 1, x minus 1. Again, though, from that one, negative 1, that is an asymptote. Positive 1 is a hole. So I would say the interval would be negative infinity to negative 1. And I'm using union symbols here. And then from negative 1 to 1. And then 1 to infinity. So those would be the intervals on which that function would be continuous. Okay, questions about that? These other two are also rational. Same thing. This one, you have 1 over x plus 2, x minus 2 is what that factors to be. So it is not continuous at negative 2. It is not continuous at 2. So we would say negative infinity to negative 2, negative 2 to 2, 2 to infinity. That would be where the graph would be continuous. And then that one would be the same thing, because the denominator, you just got t rather than x, but it's still the same thing, same denominator. So that would be the exact same as that one. All right, so any questions about that? All right. A few more here. All right, complete the steps for the functions. Use the continuity checklist to show that f is not continuous at the given value of a. Determine whether f is continuous from left or right. State the intervals of continuity. Okay, let's just have one of these. So what's going on at 1? Is it continuous or not? Okay, so A, the continuity checklist. All right, so for A, f of 1 is defined. It is equal to 4. All right, so if I plug 1 in, x is greater than or equal to 1. I plug 1 into this one, and I get 4. Okay? And then I take the limit as x approaches 1 of the function from the left. I take the limit as x approaches 1 from the right. And then I determine what's the limit then as x approaches 1 of f of x. Okay? So from the left, right, so from the negative side, when x is less than 1, if I plug 1 in there for x on the top one, that should be approaching 2 from the left. Right, from the right, x is greater than 1 on the bottom, so that should go into this one, which we've already said would be 4. So the limit as x approaches 1, since they are not approaching the same thing from both sides, what do I say about the limit? Does not exist. Okay? So since when f is 1 is equal to 4, the limit as x approaches 1 does not exist, then f is discontinuous at 1. Okay. Now, right or left? Okay, notice, so that's the A part, all right. B part, is it continuous from the right or left anywhere? All right. Well, just notice x is greater than or equal to 1 on this one, right? Correct? So, would that be from the left or the right as it approaches 1? So when x greater than or equal to 1, so that means you'll be coming from this way toward 1, so you'll be coming from the right. And since x is equal to 1 there, then you could say it is continuous from the right. At a equals 1, okay? I guess you could say the limit as x approaches 1 from the right would be 4, okay? And then C, you want to state the intervals in which it is continuous, all right? So, negative infinity up until you get to this one, all right, which would be 1, all right, because we're listing the x's, right? So negative infinity to 1, and then 1 to positive infinity. So again, we have said it is continuous from the right because you've got an endpoint there at 1. So that's why I would use the bracket there because of the bottom one. Okay? So that would be the A, B, and C on that one. Any questions about that? Okay, look at those two. Okay? So the top one is a square root, bottom one's a cube root. So looking at that, thinking about the continuity, Are either of those continuous everywhere? If I've got a square root, is there anything I cannot put under that square root? A negative, right? That one is not continuous everywhere. What about a cube root? Can I put a negative under a cube root? Yep. This one's continuous everywhere. You can plug anything you want to in for x, and it's going to be continuous. That one I'm going to go ahead and say it is continuous from negative infinity to infinity. Okay? That one, though, I have to know when 2x squared minus 16 is greater than or equal to 0. All right? So, all right, how do I do that? Well, I would be careful just adding 16 dividing by 2 because it's an inequality. It's not an equation. What you would normally do, you might could look at it and just tell, what it would be. But as far as algebra goes, what you could do, you could factor out a 2. And then from there, you can get your critical numbers, which would be negative root 8 and root 8, right? That's what would make it 0, root 8 and negative root 8. And then test a point, right? So if I say I take 0 and I test 0, be sure that's what I'm getting here. Yeah. If I test 0 right here in the middle, then I would say 0 minus 8 is negative times 2 is a negative greater than or equal to 0. A negative number is not greater than or equal to 0. It is less than, right? So the solutions are not between the two. You could test a point over here and here, but you're going to see that they're going to be going this direction. So all the x's that are either negative root 8 or less or root 8 or higher is what will make this be true. So the intervals that it is continuous would be from negative infinity to negative root 8, including negative root 8, and root 8 to positive infinity. Okay? And that one you could say it is continuous from the left at negative root 8, and you could say it is continuous from the right at positive root 8. Okay? Questions about that? Now, the fractional exponents, right? If I've got, like say on the bottom, the 2/3, what does the 3 represent? The 3 means what? Cube root. 2 means exponent 2. So I could rewrite that as the cube root of 2x minus 3 squared. That's the same thing. All right. Well, for a cube root, is there anything that I can't have under the radical? No. This one is continuous everywhere. Okay? Now, the top one up there, if I rewrite it, I get the square root of t squared minus 1, square root of t squared minus 1 cubed. Okay? That one, yes, I cannot have a 0 under there or a negative, and it's possible since it is cubed. Right? So I would do that one the same way that I did that one right there. Okay? And you will find negative 1 and 1, and it's going to be 1 and greater, or negative 1 and less. Is what's going to work for that one as well. So, any questions about those two? Okay, so we have that one. All right, well, go back to your graphs. Okay, where are the vertical asymptotes at cosecant? They are the same as at cotangent. They're at 0, pi, 2 pi. Okay. It is a reciprocal of sine, so if I draw a sine graph here, this is what I get. And it would go like this, and like this. And the same thing on the other side, right? So it is continuous on intervals of the form k pi up to k plus 1 pi, because they're always 1 pi apart, the intervals are. So you can go 0 to pi, pi to 2 pi, 2 pi to 3 pi, 3 pi to 4 pi. That's where it will always be continuous, where k is an integer. Okay. Now the limits it wanted us to do, the limit as x approaches pi over 4 of the cosecant of x. Well, pi over 4 is not a multiple of pi, so there's not an asymptote there. So just plug it in. Cosecant of pi over 4 should give you root 2. Okay? The limit as x approaches 2 pi from the left. Okay, well, here is 2 pi. There is a vertical asymptote at 2 pi. So as it approaches 2 pi from the left, what is the y value doing? Down, 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 right? So that one would be negative infinity. Okay? Questions about that? All we're trying to do is say, where is this continuous? All right? Well, it is continuous anywhere that the bottom is not 0. What makes the bottom 0? If e to the x is equal to 1, right? So what is x there? E to what power will give me 1? 0. Right? So when x is 0, that is where you have a vertical asymptote on that one, right? So I would say continuous from negative infinity to 0, and then 0 to positive infinity. Okay? Questions about that? Okay, one more of those. F of x equals e to the 2x minus 1 over e to the x minus 1. Okay. Again, when e to the x is 1, that's when it is not defined. So it is continuous again from negative infinity to 0 and 0 to infinity. Okay. Now, I did not do the limits here, and they did have some limits with these, and let's look at those real quick. So the limit as x approaches 0 from the left of e to the x over 1 minus e to the x. And then the limit as x approaches 0 from the right of e to the x over 1 minus e to the x. Okay, so we know there's an asymptote there at 0. Okay, now we could graph it if we wanted to, but let's do it analytically. Let's don't just look at a graph. All right, so up for this one. So if this is approaching 0 from the left, okay, then e to the x power. E to the x power is always going to be what? Positive or negative? Always positive. You cannot make that be a negative no matter what you plug in for x. So this is always a positive. Same thing there. Okay. Here, e to the x is always positive, but when it's coming from the left and that exponent's a negative, then this is actually going to be a fraction here. Let's see, from the left, a negative. This will be a fraction, so if I say 1 minus a fraction, what is that? That's a positive, right? 1 minus any fraction is a positive. Okay? So positive over positive, that should be approaching positive infinity as it approaches 0 from the left. Okay? As it approaches 0 from the right, okay, then e to a power bigger than, if it's e the first power, it's 2.71, which is bigger than 1. So e to the 0 power is what gives you 1. So anytime x is bigger than 0, it's going to be a number bigger than 1. So if you say 1 minus a number bigger than 1, what sign is that going to be? Negative. Positive divided by negative is a negative. Should be approaching negative infinity from that direction. Okay? Questions about that? Okay. This one we had a limit as x approaches 0. What's happening? Now, one little thing on this one. If you notice e to the 2x minus 1, what does this kind of look like on the top up here? It looks kind of like a difference of 2 squares. All right? So you could factor it like it's a difference of 2 squares. You could say e to the x plus 1, e to the x minus 1. Okay? And then these would cancel. So the limit as it approaches 0 should be the same as this one. E to the 0 is 1. 1 plus 1 is 2. There you go. Okay? Okay, so the only thing on the test, the intermediate value theorem is not on the test, and the removable or continuities, that kind of thing, is not on the test. Okay? So what you need to do, what the last problem that I did, that's like this last one that's on this review right here on 43. Okay? So I've covered everything that will be on the test. Okay? The only thing left is intermediate value theorem, which you actually do in pre-calculus normally when you're doing polynomials. And just 2 problems about removable continuities. And there's a few pictures here in the notes. Removable and non-removable, and you've got what they're called a jump discontinuity and an infinite discontinuity. So that's those last 2 homework problems. I think you can probably do those without me working any. Those are really not that big a deal. So everything on the test we have went over. Okay. So, but the main thing is look over this review and study. Okay. Any questions about the test or anything? Okay, theorem 2.16, intermediate value theorem. Suppose f is continuous on the interval a to b, and L is a number strictly between f of a and f of b. Then there exists at least one number c in AB satisfying f of c is equal to L. Alright, so let's look at what this is talking about here. So just notice when it says the interval a to b, which is closed interval, and then we have this open interval here from a to b. That's talking about your x-coordinate. So you've got an x-coordinate here at a and x-coordinate at b. Alright, and then L is a number strictly between f of a and f of b. Well, f of a and f of b are both y values. So then there exists at least one number c in AB satisfying f of c is equal to L. Okay, so on some interval there, if what he's saying is that if the function is continuous, which meets the definition that we've already talked about as far as a function being continuous on a certain interval, then there has to be a number L, a value between f of b and f of a if the function is continuous. So these first 2 are examples of that. if the graph looks like this and it's continuous, then that means there's got to be some value between f of b and f of a, which is L, at some c value. Same thing is true in the second one. On the second one, we've got 3 different x values that correspond with L. That's between f of a and f of b. The function is continuous, so that's true. On the third one, here's an example of one that's not, where the intermediate value theorem would not show a value between L, because the function is not continuous. So notice between here at this point right here, you've got a break in the graph. So there is no value of L guaranteed there because the function is not continuous. Okay? So we've got 2 problems here to look at involving the intermediate value theorem. All right, so first, A, use the intermediate value theorem to show that the following equations have a solution on the given interval. And then we're going to use a graphing utility to find the solutions to the equations on the interval. And then we're going to illustrate the answers with an appropriate graph. So first we'll notice that f of x equals 2x cubed plus x minus 2 is continuous everywhere because it's a polynomial function. So I would say f of x equals 2x cubed plus x minus 2 is continuous everywhere. Okay. So it is continuous on -1 to 1. Okay. And then if we plug in these endpoint values, okay, so if I say f at -1 and I put -1 in the place of the x's and then figure out what that equals, that will equal -5. And then if I put 1 in for x, I will get 1. Alright, so the intermediate value theorem guarantees a number c between -1 and 1, where f of c is equal to 0. Okay. One of the values is negative, one of the y values is negative, one of the y values is positive, so there has to be a f of c equals 0 between the two. Okay. Which would be where the solution to the equation is at. All right. Next thing it wanted us to do was use a graphing utility to find the solution. So if you've got a graphing calculator like this one, all right, then what we can do is, all right, so what you're going to see first is the blank screen. So hit y equals, and then put this equation in to graph as a function. So we'll say 2x to the 3rd power plus x, whoops, this is a newer one here. Okay, so I need to hit my right arrow key to get off of the exponent there. Now plus x minus 2. So there's the function. Alright, you might want to check your window. This is where my window is set, -5 to 5 on the x and -5 to 5 on the y. And then you hit graph, and it will graph the function. Alright, and I want to know, well, what is an estimate for that 0? Okay, so what you can do with the calculator is hit calculate here. It's above trace, so I'm going to hit second trace button. Choice 2 is 0. And now I've got to kind of set a bound. In case there's more than one 0, then you've got to set a bound around it. So I'm just going to say 0 for the left bound and 1 for the right bound. And then you can guess, I'm just going to hit enter, and it gives me the 0 is around 0.3512235. Okay, so what I would put here then for the B part is C is around 0.835. Alright, let's do the same thing for this next one here. Okay, so for this one, the function would be f of x equals, so I have to think of that as being equal to 0 if I want to graph it. So let's do this. Okay, so that's the function I would be thinking about. Alright, so it is continuous on from 0 to 1. Alright, right here where the interval is at. Okay. Because if I plug 0 into this, I'll get a positive. If I plug 1 in, I get a positive. So I know, and the numbers between that would work the same way. Now you could get a negative under the radical there maybe, but you don't have that between 0 and 1. So it's definitely continuous there. Alright. So now if I plug in f of 0, then I will get square root of 10 minus 5. Alright, square root of 10 is less than 5. So that is a negative number. That is less than 0. If I put in 1, I get 1, which is greater than 0. So I have a negative when I plug in 0. I have a positive when I plug in 1. So therefore the intermediate value theorem guarantees a number C between 0 and 1 where f of C is equal to 0. Okay. Now same thing, we can get an estimate there. So let's go to our calculator, and this time I want to change that to the square root of x to the 4th plus 25x cubed plus 10. Then I'm going to get my right arrow key and get out of that front of that radical and hit minus 5. Alright, I'm going to hit graph and let's see what we've got. Okay. So for my 0 there, I'm going to hit second calculate. Go down to 0. My left bound, I'm going to let be 0. My right bound, I'll let be 1. I'm going to guess. I don't know what to guess for. Alright, so 0.8342548. So I would say C would be around 0.834. Alright, so that is the intermediate value theorem. Alright, one more thing in this, from this section, this video. We can classify discontinuities a little bit more with some different words. Alright, so the main two words is removable and non-removable. Okay, and these first two are examples of removable. So if there's a hole in the graph, and in other words the limit exists at A, but it's not the same as the function value at A, which would be here and here. Here the function value would be up whatever this one is, but it's not the same as the limit as x approaches A. That is called a removable discontinuity. Okay. Non-removable would be if the limit does not exist at A, which would be true here and here. Here we've got a jump, and here we've got an asymptote. Okay, so again, the first two are called removable discontinuities. The second one here, they're calling this a jump discontinuity because the function is jumping from here to here and then continuing. For the second one, we've got an asymptote there, so they're calling this an infinite discontinuity. Alright, so let's just take two problems here and let's see if we can figure out what those would be. Alright, so classify the discontinuities. Alright, so I know at x minus 2 it looks like I would have something going on there. Okay, it's not defined at 2. So let's factor it and see if it's a whole or if it is a vertical asymptote. So if I factor the top, I get x minus 2, x minus 5. And I can see here now that the x minus 2 is the same, have a factor of x minus 2 on the top, and the denominator is x minus 2. So that is going to be equal to the line x minus 5 everywhere except where x is 2. So the graph of that would just be a line with a hole in the graph at x equals 2. So the limit would exist as x approaches 2. The limit would be -3, but f of 2 does not equal that. It is undefined there. So that would be a removable discontinuity like this first one up here. So I would say removable discontinuity at x equals 2. Okay. Now same idea on this one. Let's see what we've got here. So I'm going to take this function. I'm going to first factor an x out of the top. And then I'm going to factor that a little more and see if I've got a factor of x minus 1 in there with it. Which I do not. I get x minus 2, x minus 2. Alright, so x has a factor in the numerator and denominator. So therefore, when x is 0, which is what the 0 is at x there, I have a hole in the graph. When x is 1, I have a vertical asymptote. So here I would want to say I have a removable discontinuity at x equals 0, and then I have a discontinuity that is not removable at x equals 1. And more specifically, we could call it an infinite discontinuity because it is a vertical asymptote.